Intel patent reveals new XBM memory architecture that ditches HBM's costly silicon interposer. The leverage shift starts now. Here is the signal that separates noise from actionable change. We will map trigger, incentive shift, and downstream impact before the close. That part is the silicon interposer, the middleman between your GPU and its memory stack. What Intel is proposing instead is called XBM, or backend-transistor DRAM. And if this works, it rewrites the economics of AI hardware overnight. Here's the problem everyone's been living with. HBM, high bandwidth memory, is the standard for AI chips and data center GPUs right now. NVIDIA, AMD, everyone uses it. But HBM requires a silicon interposer, essentially a silicon wafer that acts as a bridge between the GPU and the memory stack. That interposer is expensive to manufacture, adds thermal complexity, and increases the overall cost of the system. For a single H100 GPU, that interposer can cost hundreds of dollars. Scale that across millions of chips, and you're looking at billions of dollars in annual spend across the industry. Intel's patent describes a radically different approach. Instead of stacking memory on top of a chip and connecting it through an interposer, XBM moves the memory transistors to the back of the die itself, literally integrating them into the substrate. Think of it as removing the middleman entirely. The memory cells sit directly under the logic, connected through a back-end interconnect layer. No separate interposer needed. Why does this matter? Cost, first. Eliminating the interposer removes one of the most expensive manufacturing steps and materials costs in the supply chain. For data center operators and chip makers, that's a direct margin improvement. NVIDIA and AMD are selling GPUs at premium prices partly because HBM costs so much. If Intel can deliver equivalent bandwidth at significantly lower cost, that changes pricing power overnight. Second, thermal and power efficiency. An interposer adds thermal resistance and parasitic power loss. Moving memory directly to the backend reduces both. For AI workloads that are already power-hungry and thermally constrained, that's material. A 10 to 15% power reduction on a data center scale translates to massive operational savings. Third, and this is the contrarian angle, this doesn't kill HBM. It supplements it. HBM will still dominate for the next 3 to 5 years. But XBM represents a credible alternative pathway, and that's what breaks NVIDIA's supply chain lock-in. Right now, if you want the fastest AI chip, you have to accept HBM and pay NVIDIA's prices. If Intel ships XBM and it performs comparably, suddenly NVIDIA's margin advantage shrinks. AMD gets a new lever to compete. And customers get optionality. Here's what changes next. First, watch the patent claims carefully. The real competitive moat isn't the idea, it's the implementation details. How Intel bonds the back-end layers, how they manage thermal expansion, how they achieve yields. If Intel can manufacture this at scale reliably, they've got a genuine advantage. If yields are poor or thermal management fails, it's a paper advantage. Second, look for licensing. Intel doesn't need to be the only manufacturer of XBM. If they license this to TSMC or Samsung, suddenly every chip maker has an alternative to the expensive interposer path. That's when the real disruption happens. Third, timeline matters enormously. This is a patent, not a shipping product. Intel would need to integrate XBM into their data center GPU roadmap, test it at scale, and prove yield rates. That's at least 18 to 24 months out, probably longer. By then, NVIDIA will have moved on to its next generation and locked in even more of the market. But if Intel can show a credible working prototype in the next 12 months, that shifts investor expectations about data center competition. For investors in NVIDIA and AMD, this is a watch-and-wait moment. NVIDIA's dominance is partially built on exclusive access to the most advanced memory architecture and process nodes. If that advantage erodes, even partially, valuation multiples compress. For Intel investors, this is proof the company is still innovating on core microarchitecture, not just playing catch-up. For data center customers, the signal is clearer: competition is coming. HBM pricing power will peak soon. By 2026 or 2027, if XBM ships and proves reliable, you'll have options. That means negotiating leverage returns to the customer. The real insight here is this: the most valuable part of the AI infrastructure stack isn't the chip logic anymore. It's the memory subsystem. Intel's patent is betting that whoever controls the memory architecture at the lowest cost wins the next generation of data center competition. That's a smart bet. Whether they can execute on it is the only question that matters now. Watch for prototype announcements in the next 12 to 18 months. That's when you'll know if this patent becomes a product or stays a footnote. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next. Watch the execution timeline, second-order market effects, and policy response to gauge what happens next.